The word significant refers to something meaningful or important. More formally, the Oxford Dictionary defines it as sufficiently great or important to be worthy of attention. Mathematically, significant figures refer to which digits in a number or measurement are important or meaningful in terms of the precision of the recorded or calculated value. All measurements are only approximations, being subject to some degree of error, including but not limited to the precision and accuracy of the instrument being used. We will investigate these further in a separate video. For the purpose of this topic, we assume that our measurements come from accurate instruments, so we can usually determine the precision from the recorded value. Significant figures tell us how many of the digits are certain, coming directly from the instrument, and the last estimated digit as well. In other words, the very last digit has either been rounded to the smallest unit on the instrument or estimated based on the position of the measurement between two markings on the instrument. For example, this nail has been measured as 3.6 centimeters, correct to the nearest tenth of a centimeter. Both digits are clearly important, and we can say that this measurement is correct to two significant figures. Even writing it as 36 millimeters, clearly we still have two significant figures. We could convert the measurement to other units depending on the chosen metric prefix. It could be written as 0.036 meters without any prefix. 4 digits are written, but only the same two are significant. We could even write the same measurement as 0.000036 kilometers. Not that we would choose to do so. And for those already familiar with scientific notation, writing it in this form has its advantages, including the fact that the number out the front is typically written with the correct number of significant figures. This leads us to an important conclusion. Leading zeros at the front of a number are merely place value holders and will vary depending on the metric prefix being used. In other words, zeros at the front of a number are not counted as mathematically significant. What happens if we use even smaller prefixes? This will make the number larger, with zeros required on the end. Are these zeros significant? Well, it depends on the precision of the measurement. Let's investigate further. Consider a length of 3 centimeters. Writing 3 centimeters only suggests a measurement correct to the nearest centimeter. And since we've only written one digit, then we clearly only have one significant figure. This is a common mistake when writing values that are conveniently equal to a whole number value. In reality, this measurement was likely to have been 3.0 centimeters. Now we see that it has again been measured to the nearest millimeter, and we have two significant figures. The 0 on the end of the decimal serves to show how precise the measurement was. This leads us to conclude that zeros written on the end of a decimal must be counted as significant. But this measurement can also be written as 30 millimeters. So the 0 on the end of the whole number here is clearly important too, since we measured to the nearest millimeter. Will this apply to any zeros on the end of a number? Let's assume the nail was only measured to the nearest centimeter, so 3 centimeters is the correct value and shows only one significant figure. However, converting this into millimeters still gives us 30 millimeters. Now we're confused, or misled at the very least. The measurement was not to the nearest millimeter, so the 0 this time is not counted as significant. We have discovered that zeros require special consideration when determining significant figures. We will formalise our findings in a moment, but there's still one case we haven't considered. We already know that 3.15 metres, which is 315 centimetres, has 3 significant figures, being recorded correct to the nearest centimetre. Similarly, 3.05 metres is equal to 305 centimetres, still recorded correct to the nearest centimetre, so it still has 3 digits which are significant. Now we see that zeros in between non-zero digits are still significant. Of course, converting this to millimetres gives us 3050 millimetres, and once again the zero on the end is not significant unless we measured it to the nearest millimetre. Hopefully it's now apparent to you that the only time we aren't sure whether or not zeros are significant is when they appear on the end of whole numbers. Zeros at the front are not significant, zeros in between other digits are significant, as are zeros on the end of decimals. We've talked only about measurements and how the precision determines the number of significant figures. The concept is similar with counting. We simply need to know how the number was rounded. Consider a crowd in a stadium watching a sporting event. An announcement might say that 28,000 people were in attendance. We cannot tell whether this number has been rounded to the nearest 1,000, the nearest 100, or the nearest 10, or not at all. The zeros on the end may or may not be significant. If they had said 27,999 people are in attendance, then it's obvious that everyone had been counted, so all 5 digits are significant. So if one more person enters the stadium, we would have 28,000 people, with all 5 digits being significant. Looking at 28,000 without this extra information, we cannot tell how precise the value is. We can summarise our findings in 3 easy-to-follow steps when counting significant figures. Step 1, from the left, always go to the first non-zero digit. In this example, we would start counting here at the 1. Step 2, all digits that follow are significant, except the uncertainty of zeros on the end of whole numbers. Our example is not a whole number, so all remaining digits are significant. We have 6 significant figures. This is usually abbreviated to 6 sig fig. And step 3, zeros on the end of whole numbers might be significant. Further details would be required. In this example, we definitely have 2 significant figures, the non-zero digits. But there could also be 1, 2, or 3 of the zeros on the end that are also significant. We can't tell yet until we are told the precision of the measurement or any rounding that has been applied. Pause the video if you'd like to try these on your own first. In number 1, all 4 digits are significant since there are no zeros, and similarly in number 2. In example 3, we see the same 4 digits, but this time with a leading 0, which is not counted as significant, so there are still only 4 significant figures. In number 4, there are more leading zeros, which we can still ignore, but the extra 0 on the end of the decimal makes it more precise, giving us 5 significant figures. In number 5, all 4 are significant, remembering that zeros in between non-zeros are significant. In number 6, it's a special case. Zeros are on the end of a whole number. No further details are provided, so they may or may not be significant. We cannot tell for sure. We can say that it definitely has 2 significant figures and might have 3 or even 4. If we were told that it is correct to the nearest 10 here, then we would know it has 3 significant figures. In example 7 and 8, we have decimals, so we ignore the leading zeros, but everything else is significant, giving us 4 significant figures in both cases. Now that we know how to count significant figures, we need to be able to round our answers to the required number of significant figures after performing various calculations. The good news is that the technique is the same as rounding decimals, or whole numbers, except that we look at the digit after the required number of significant figures instead of decimal places. So we round up if the next digit is 5 or higher, otherwise we leave it as it is. Either way, we discard all the extra digits unless it's a whole number, in which case we change the extra digits into zeros. These will be place value holders and are zeros on the end of a whole number that we know will not be significant. This is why we should state the number of significant figures after our answers, so other people will also know. Consider this calculator display. Assume we need to round our answer to 3 significant figures. Here are the first 3 significant digits. We simply need to decide whether they remain as they are or whether the last digit will go up by 1. Our rounded answer is either 4.17 or 4.18, whichever the displayed value is closest to. Clearly it is closer to 4.18, but looking at the next digit, we see it is a 6. So being 5 or higher, it tells us to round the 7 up by 1 to an 8. It's good practice to state the rounding that has been applied when giving your final answer. In this display, the third significant figure is a 0, and the next digit is only a 4. So we are less than halfway from the 0 to the next possible digit, a 1. So we leave it as it is. The number is closer to 0.0580 than it is to 0.0581. Let's round our earlier examples so they only have 3 significant figures. In the first one, the first 3 significant figures are here. This 8 makes the 6 change into a 7. We can't discard the last digit since it's a whole number. 517 is not even close to 5,168, so we need to change it to a 0. Our answer is 5,170, correct to 3 significant figures. Clearly, the original value is closer to 5,170 than it is to 5,160. In example 2, we have the same digits, but this time it's a decimal, so we can discard the extra digit, giving us 5.17. The same goes in number 3, so the answer is 0.517, and number 4 gives us 0.00517. Number 5 is a whole number again. The 8 forces 0 to become a 1, but we need to replace the 8 with a 0, giving us 5,110 to 3 significant figures. Example 6 already has 2, 3 or 4 significant figures depending on whether or not the zeros on the end are significant. With 3 significant figures, the first 0 will be significant, but the last one will not be. Stating 3 significant figures after the answer clarifies this for anyone reading the solution. In number 7, the 0 after the decimal is the 4th significant figure. Removing it gives us 3 significant figures. Similarly, in our last example, the extra 0 on the end needs to be truncated, leaving these 3 as the significant figures. Here are some examples for you to try. Round them to have only 2 significant figures. The first becomes 21 since the 2 is clearly less than 5. In number 2, we have 3 digits but require only 2 significant figures. The 4 means that we do not round the 2 up, we leave it as it is. However, we need to place a 0 where the 4 was. In other words, 324 is closer to 320 than 330. Without the 0, it would look like 32. Next, the 2 significant digits are the 1 and the 8. They are followed by a 6, so we round the 8 up to 9, giving us 0.019. The next one is very similar. except it is a 9 that needs to be rounded up. It's probably easier to think of it as being 19 rounding up to 20, giving us 0.020. Number 5 becomes 0.38 since it's only a 1 that is the next digit. In example 6, the 4 and the 9 are our two significant digits, but the 7 after them makes the 9 go up by 1, in turn making the 4 go up to 5. It's easier to think that 49 goes up to 50. We also need all these zeros to hold the place value columns of the other non-significant digits, giving us 500,000 to two significant figures, which is to the nearest 10,000 in this particular example. Next, the first two 9s are significant, followed only by a 1, so they remain as they are. And lastly, again with two 9s, but this time followed by a 5. We need to think that 99 rounds up to 100. However, this gives us three significant figures. We only want two, so we need to drop the extra 0 from the end of the decimal, giving our answer as 0.0010. This final example illustrates that there are occasions when adhering strictly to significant figures may not be warranted. A height of 99 centimetres is really the same precision as a height of 102 centimetres, yet it only has two significant figures compared to three. We would keep this in mind when using this data. Fortunately, at school at least, you are most likely to be told how many significant figures you should use in your answer. We will investigate the intricacies in dealing with measurements and the validity of calculations in the separate topic, error in measurement. However, there are some general rules of thumb you can use if you need to decide how to round your final answer. The overriding concept is simple. You should never give an answer that is more precise than the data you used in the calculation. So we need to round to the same level as the least accurate information used. If you follow this general guideline, you should mostly be fine, but be sure to state the rounding applied with your answer. More scientifically, the suggested rounding actually depends on the mathematical operations being performed with the measured values. If only additions and subtractions are performed between measurements, then we should give our answer to the least number of decimal places used in the calculation. This represents the least precise value and avoids the problem of losing significant figures as discussed with the 99 centimetres versus 102 centimetres. Adding these heights gives a total of 201 centimetres to 0 decimal places, but would only give 200 centimetres to two significant figures. If multiplying or dividing the measurements, then the answer would be given according to the least number of significant figures. 99 multiplied by 102 gives 10,098 square centimetres, which is 10,000 square centimetres, correct to two significant figures. To fully appreciate why this is necessary, you will need to study the topic error in measurement. If these measurements were more precise, say 99.0 multiplied by 102.0, then three significant figures would give a more precise answer of 10,100 square centimetres. Let's end this video with a brief application of these two rules. We will calculate the perimeter and the area for this rectangle. When calculating the perimeter, we can only use one decimal place in the answer, despite one length being provided to two decimal places. So our answer should be given as 37.3 centimetres, correct to one decimal place, which is the nearest millimetre. This is why it's so important to write down the correct precision of all measurements. Perhaps these were all actually measured to two decimal places, in which case 5.7 should have been recorded as 5.70, and we could then use the full answer, 37.34 centimetres. For the area, we have two significant figures multiplied by four significant figures, giving us 75.639, which is too precise for the measurements used. Rounding to two significant figures to match the least precise measurement gives us 76 square centimetres. Using 5.70 would have allowed an answer of 75.6 square centimetres, being correct to three significant figures. If in doubt, remembering to round to one decimal place and stating that you have done so should be sufficient until you study higher levels of maths, science or engineering, or at least until you encounter the error in measurement topic.